So this is the iGCSE topic introduction to magnetic effects. So what have we got? Well, we've got the right hand grip rule for magnetic behavior. So there's your right hand, has to be right hand. Electric current in a conductor produces a field around it. So when electrons flow in a wire, we create a circular magnetic field that will make a plotting compass turn in a circular direction as you move it round. You think, okay, big wow, what does that do? Well, what we can do is if we take lots and lots of loops of wire or turns, we can add up all the right hand grip rules on one side and on the other side. So remember, the wire on this side comes out the page and it goes into the page and out the page and into the page. So because you're turning your thumb, thumbs up, thumbs down, thumbs up, thumbs down, all of those field lines reinforce to create what looks like a bar magnet. And we call this a solenoid. Now then what we can do is make that into an electromagnet. So an electromagnet is made from an iron core, typically, or a nail. We do lots of turns of insulated wire around the core, and the current then flows around the wire, not in the nail at all, just around the wire, because remember we said it's insulated. That induces a magnetic field in the core, and that can be used to create moving parts in a system. So it could be, for example, here we have an electromagnet, and this is a funny one. It's basically like a U shape, but it's still an electromagnet. It's just been basically made into a horseshoe shape. When I turn the battery on, the north and the south both attract the iron contact. It breaks the circuit, and the hammer moves gong, and then it comes back again because the circuit's broken. The current turns off. The electromagnet's gone off because we can make it turn on, off, on, off, and so we've got effectively an electromagnetic effect. We can do things like the motor effect, where that's current passes through the wire, and the wire then experiences a force due to Fleming's left-hand rule we talked about. So force, F, B, magnetic field, I, current, or direction of force, magnetic field, direction of current. If a wire has a current flowing through it, and it's in a region of space where there's a magnetic field, it will get pushed out. And the force is up if the current flows that way. But if the current flowed the other way, the force would be down. So you can make children's toys, electromotors, that kind of thing. And you can make a loudspeaker. So this is a little bit complex. So magnet, a bit of a weird one because it's like a bit of a bucket. And then the middle of it, because remember this is a slice, a flat slice of it. So it's like circular, but in the middle is the south, on the outside is the north. So what happens is we caught some wire around a cone, and when you get an alternating current in the coil, it pushes and pulls the paper cone backwards and forwards, which pushes and pulls the air molecules backwards and forwards, which creates a sound wave. We can also, of course, have motors. So electric motor here, we've got carbon brushes, a split ring commutator. So there's a split, which means that as it spins, as we get a push, it doesn't tangle up the wires, and these little carbon brushes will wear away over time and can be replaced. In a car, you would see that, some of these old-fashioned devices. And the clever bit with this is, although the field is that way, because the coil of wire, the current flows up one way and down the other, due to Fleming's left-hand rule, the force reverses. So force up, current towards us, current away from us, and force down. So there you go. That is electromagnetic effects.